In the middle of the Cold War, the US did something unthinkable. They detonated a nuclear bomb in space. But what happened next wasn't expected. Strange lights filled the sky, satellites failed, and something about the experiment went completely off script. The Cold War context. Why nuke space? The decision to test a nuclear weapon outside Earth's atmosphere did not come from curiosity alone, and it did not emerge in a calm or neutral period of history because it was shaped by a time when global tension was high, fear influenced strategy, and scientific exploration was deeply tied to military goals, all of which defined the intense environment of the Cold War, a prolonged period of political and technological rivalry between the United States and the Soviet Union, where each side constantly tried to gain an advantage not only on Earth but also in the newly opened domain of space. And this atmosphere of competition and uncertainty created the conditions that made something as extreme as detonating a nuclear device in space seem not only possible but necessary within the logic of the time. During this period, both nations were driven by a deep sense of urgency that came from the fear that the other side might develop a decisive technological advantage first. And this fear was not abstract or distant, but immediate and pressing, because the existence of nuclear weapons meant that any major imbalance in capability could lead to catastrophic consequences. So decisions were often made quickly and with limited long-term understanding, as leaders and scientists tried to anticipate threats that had never been fully explored before, especially in areas like high altitude and space environments, where there was very little prior knowledge to rely on. One of the central fears influencing these decisions was the possibility of electromagnetic pulse, often referred to as EMP, which was understood as a powerful burst of energy that could disrupt or destroy electronic systems over a wide area. And while the basic idea of EMP was known, its full effects were not yet understood, particularly in the context of space, where the absence of atmosphere and the presence of Earth's magnetic field could change how such energy spread and interacted with technology. And this uncertainty made it essential, from a military perspective, to test and observe these effects directly, rather than rely on theory alone. At the same time, there was growing concern about missile interception strategies because both the United States and the Soviet Union were developing long-range missiles capable of carrying nuclear warheads across continents, and the ability to detect, track, and potentially disable these missiles before they reached their targets became a critical area of research, which led scientists to consider whether nuclear detonations in space could interfere with or even destroy incoming missiles, either through direct energy release or through secondary effects like radiation and charged particles. And this line of thinking further reinforced the idea that space was not just a place for exploration, but a potential battlefield that needed to be understood in detail. The pressure to act was intensified by the early developments of the space race, particularly after the launch of Sputnik 1 by the Soviet Union, which marked the first time a human-made object successfully orbited the Earth and demonstrated a clear technological capability that had immediate military implications. Because if a nation could place a satellite into orbit, it also had the ability to deliver payloads over long distances, and this realization caused a strong reaction in the United States, where leaders and scientists recognized that they were not only competing in scientific achievement, but also in strategic positioning. The launch of Sputnik 1 created a sense of urgency that extended beyond pride or prestige, because it suggested that the Soviet Union might be ahead in key areas of rocket technology and space capability. And this perception drove the United States to accelerate its own programs, leading to increased funding, rapid experimentation, and a willingness to explore ideas that might have seemed too risky or extreme under different circumstances, including the idea of using nuclear devices in space as a way to gain knowledge that could not be obtained through any other means. Within this environment, scientists were not acting independently of military goals because their work was closely connected to national defense priorities, and many of the questions they sought to answer were directly linked to how nuclear weapons might behave in conditions that had never been tested before, such as the near vacuum of space, where there is no air to carry shockwaves in the same way as on Earth, and where energy might instead spread through radiation and electromagnetic effects in ways that could have wide-reaching consequences. The key point that guided these efforts was the need to understand what happens when a nuclear weapon detonates outside Earth's atmosphere, because without direct testing, there was no reliable way to predict the outcome, and theoretical models at the time were limited by both computational power and incomplete knowledge of space physics. So scientists and military planners believed that real-world experiments were necessary to fill these gaps, even though the potential risks were not fully known or understood. This desire for understanding was not purely academic, because the results of such tests could influence how weapons were designed, how defenses were planned, and how future conflicts might be fought or avoided. And in this sense, the decision to conduct these experiments was tied to a broader strategy of deterrence, where each side aimed to demonstrate capability and preparedness in order to discourage the other from taking aggressive action, which meant that knowledge itself became a form of power, and gaining that knowledge quickly was seen as essential. The idea of detonating a nuclear device in space also reflected a shift in how people thought about warfare and technology, because it extended the potential reach of conflict beyond the surface of the Earth into a new domain that was not yet governed by clear rules or agreements. And this lack of established boundaries made it easier for such ideas to be pursued, as there were fewer constraints and less precedent to limit what could be attempted, especially in a context where both sides were racing to explore and control as much of this new domain as possible. At the same time, the scientific community was aware that space presented unique conditions that could reveal new information about fundamental physical processes, such as how high-energy particles move through magnetic fields or how radiation interacts with different materials. And these questions were important not only for military applications, but also for understanding the natural environment of space, which was becoming increasingly relevant as satellites and other technologies began to rely on stable and predictable conditions in orbit. Operation Fishbowl, the secret series. The plan did not begin with a single launch or a single explosion, but with a quiet decision made inside a system that was already moving faster than anyone could fully control, a system driven by urgency, pressure, and the constant need to test what had never been tested before. And inside that system, a new series of experiments was approved. A series that would take nuclear weapons out of the atmosphere and push them into a region where the rules were not fully known, where prediction became uncertain, and where the line between control and chaos started to blur in ways that even the scientists involved could not completely anticipate. And that series would come to be known as Operation Fishbowl, a name that sounded almost harmless, almost contained, even though everything about it pointed in the opposite direction. Operation Fishbowl was not a standalone effort, and it did not exist in isolation, because it was part of a much larger operation that had already been set in motion, a broader program of nuclear testing known as Operation Dominic, which itself represented one of the most intense periods of nuclear experimentation ever carried out. And within that larger framework, Fishbowl was given a very specific purpose, one that focused on high-altitude detonations, on sending nuclear devices far above the Earth and observing what would happen when they exploded in a region that was neither fully space nor fully atmosphere, a region that was still being understood, still being mapped in terms of its physical behavior, and still filled with unknowns that could only be explored through direct testing. The idea behind Operation Fishbowl was clear on paper, structured around a series of planned detonations that would take place at different altitudes and under different conditions, each one designed to produce data that could be analyzed and compared, and these tests were given names that followed a pattern, names like bluegill, kingfish, and starfish, each one representing a specific launch, a specific moment, a specific attempt to gather information that had never been gathered before. And while these names might suggest a sense of order or sequence, the reality behind them was far more unstable, far more uncertain, and far more dependent on factors that could not always be controlled. Bluegill was not just a name, but a planned event, a launch that was supposed to carry a nuclear device into the upper atmosphere where it would detonate under carefully observed conditions. And the same was true for Kingfish and Starfish, each one representing a step in a larger experimental process. But from the very beginning, there were signs that this process was not going to unfold as smoothly as planned, because the technology required to carry out these tests was operating at the edge of its capabilities, relying on rockets that had to perform with precision under conditions that allowed very little margin for error. The rockets used in Operation Fishbowl were not just transport systems, but critical components of the experiment itself, because without a successful launch, there could be no detonation, and without a detonation, there could be no data, and this placed enormous pressure on each launch to succeed. Yet at the same time, the complexity of the systems involved meant that failure was always a possibility that quickly became a reality, as early attempts began to encounter problems that could not be ignored or easily fixed. When the first launches were attempted, they did not simply fail in a quiet or contained way, because failure at this level was not subtle. It was visible, dramatic, and immediate. And when a rocket malfunctioned during ascent, it created a situation that could not be allowed to continue, because the payload it carried was not just another piece of equipment, but a nuclear device. And the risk of that device falling back to Earth in an uncontrolled manner was something that could not be taken, which meant that the only option in such a scenario was to destroy the rocket while it was still in the air. This process of destroying a malfunctioning rocket was not a minor procedure, but a deliberate and necessary action, carried out through remote commands that would trigger the destruction of the vehicle before it could descend. And while this prevented a larger disaster, it also meant that each failed launch ended in a visible explosion, an event that underscored just how fragile the entire operation was, and how dependent it was on systems that were being pushed to their limits in order to achieve something that had never been done before. As more attempts were made, the pattern of failure began to take shape, with rockets experiencing malfunctions that forced them to be destroyed mid-air, turning what was supposed to be a controlled series of experiments into something far less predictable, something that began to reveal the gap between planning and execution. And this gap was not just a technical issue, but a reflection of the broader challenge of working in an environment where so many variables were still unknown. Each failed launch added to the tension surrounding Operation Fishbowl, because with each failure came the realization that control was more limited than expected, and that even with careful planning and advanced technology, there were still elements that could not be fully managed. And this realization began to shift the tone of the entire operation, moving it away from the idea of a controlled experiment and towards something that felt more uncertain, more experimental in the truest sense of the word, where outcomes were not guaranteed and where each attempt carried with it a level of risk that could not be completely eliminated. The unpredictability of these early launches was not just a matter of technical difficulty, but also a reflection of the environment in which they were taking place, because high-altitude testing introduced challenges that were different from those encountered in lower altitude or ground-based tests, including the behavior of the rocket as it moved through different layers of the atmosphere, the effects of temperature and pressure changes, and the interaction between the vehicle and the surrounding environment as it approached the edge of space. These factors combined to create a situation where even small issues could lead to significant problems, and where the margin for error was extremely narrow, and as a result, the early stages of Operation Fishbowl became defined by a series of setbacks that highlighted the limits of the technology being used, and the difficulty of carrying out such complex operations under conditions that were not fully understood. Despite these setbacks, the operation did not stop, because the need to obtain data and move forward with the testing program remained strong, and each failure was analyzed, studied, and used to make adjustments for the next attempt, creating a cycle of trial and error that gradually refined the process, while also reinforcing the idea that this was not a simple or straightforward experiment. The names Bluegill, Kingfish, and Starfish continued to represent planned detonations, but they also began to carry the weight of these earlier failures, becoming markers of an operation that was evolving in real time, adapting to challenges as they arose, and pushing forward despite the uncertainty that surrounded it. As the program continued, the contrast between the original expectations and the reality of the situation became more apparent, because what had been envisioned as a series of controlled, carefully executed tests was instead unfolding as a sequence of attempts that were subject to failure at multiple stages, from launch to detonation. And this contrast highlighted the complexity of the task at hand, as well as the difficulty of applying theoretical knowledge to practical scenarios in an environment that was still being explored. The shift in tone from controlled to experimental was not just a change in perception, but a reflection of the actual conditions under which Operation Fishbowl was being carried out, because each launch carried with it the possibility of failure, and each failure introduced new variables that had to be accounted for, and this created a dynamic where the operation was constantly evolving, shaped by both its successes and its setbacks. The unpredictability of the early launches also had an impact on the people involved, including the scientists, engineers, and military personnel who were responsible for planning and executing the tests, because it forced them to confront the limitations of their knowledge and the challenges of working in an environment where not everything could be predicted or controlled. And this realization influenced the way they approached subsequent attempts, leading to adjustments in both strategy and expectations. At the same time, the need to proceed with the operation remained unchanged, because the broader goals of the program were still in place, and the importance of obtaining data from high-altitude nuclear detonations continued to drive the effort forward, even in the face of repeated failures. And this persistence reflected the broader mindset of the time, where experimentation and progress were seen as essential, even when the path forward was uncertain. As the sequence of planned detonations continued, the names Bluegill, Kingfish, and Starfish remained central to the operation, representing the structure and intent behind the program. But the reality behind those names was far more complex, shaped by the challenges and unpredictability that had emerged during the early stages of testing. And this complexity added a layer of tension to the operation, as each new attempt carried with it both the hope of success and the risk of failure. The destruction of rockets mid-air became a defining feature of these early attempts, a visible reminder of the risks involved and the limits of control, and each such event reinforced the idea that Operation Fishbowl was not a routine or predictable series of tests, but a high-stakes experiment that was pushing the boundaries of both technology and understanding. The Starfish Prime detonation. On July 9, 1962, the world saw something that no one had ever seen before. Something that looked almost like science fiction, but was very real, very dangerous, and very human. The plan was simple in words, but impossible in reality. A rocket would launch from Johnston Atoll, a small group of islands in the middle of the Pacific Ocean, carrying a nuclear warhead into the edge of space. This was not just a normal test. The warhead itself was enormous. A 1.4 megaton bomb, far more powerful than anything most people had ever imagined. To put it in perspective, the bombs that had been dropped on Japan 20 years earlier were less than 1/10 of that size. Scientists and military planners wanted to see what would happen when such a powerful weapon exploded high above the Earth, above almost all of the atmosphere, at an altitude of about 400 kilometers. This was a place where satellites orbit today, a place that is still technically space, where the air is so thin that normal explosions behave completely differently. The expectations for the detonation were cautious. On paper, scientists predicted that the bomb would produce a brief flash, a sudden light that would last a fraction of a second, and then almost nothing else. There would be some interaction with the thin upper layers of the atmosphere, but it was expected to be minimal. The explosion was not supposed to be visible from very far away, and it certainly was not supposed to affect electronics or satellites on Earth. This was, in theory, a controlled experiment designed to gather data on a nuclear blast in a high-altitude environment, to study how radiation moved through space, and to see if such detonations could possibly be used as a weapon against incoming missiles. The calculations were careful, and the models made sense according to what was known at the time, but what happened when Starfish Prime detonated was far beyond anything anyone had predicted. The launch itself was tense. Engineers and technicians watched as the rocket lifted off from Johnston Atoll, a tiny speck of human construction in the vast Pacific. The rocket climbed higher and higher, passing through layers of the atmosphere that had never been crossed by a nuclear device. At each moment, the team at the control center monitored the rocket's trajectory, checking every system to make sure it was functioning correctly. Failures had happened before in other parts of the program. Previous tests in Operation Fishbowl had seen rockets break apart, sometimes needing to be destroyed mid-air to prevent disaster. Everyone knew that if anything went wrong with this launch, the consequences could be catastrophic. The pressure was enormous, the stakes higher than ever, and every eye was on that rocket as it disappeared into the thin air above the Earth. Then came the detonation. The bomb exploded at an altitude of 400 kilometers in what was still technically space. The result was immediate, violent, and spectacular. Instead of a brief flash, the sky lit up with a blinding light, a flash that was seen across thousands of kilometers, reaching as far as Hawaii, which is nearly 1,400 kilometers away from Johnston Atoll. People on the ground, who had no idea what exactly had happened, reported a sudden bright glow in the sky, colors they had never seen before, red, green, and purple, shimmering across the horizon. It was beautiful in a terrifying way, almost like the auroras that naturally occur near the poles, but entirely artificial, created by human hands. The sphere of charged particles from the explosion expanded rapidly, pushing outward in all directions, filling space with energy that interacted with the Earth's magnetic field in ways that had never been observed. The visual effect was only part of the story. The explosion released massive amounts of radiation and high-energy particles. These particles did not simply vanish into space. They became trapped by the Earth's magnetic field, creating artificial radiation belts that would persist for months. Satellites in orbit were suddenly exposed to levels of radiation far higher than they were built to handle. Communication satellites, weather satellites, and even military satellites began to fail. Some stopped working completely within hours or days. The explosion created an electromagnetic pulse that traveled across the Pacific, short-circuiting some electrical systems on the ground and affecting the operation of satellites and rockets. What had been expected to be a controlled test had instead become an event that impacted a vast area of the planet and space above it. Scientists who had predicted only a small contained flash were stunned. The scale of the charged particle cloud, the intensity of the light, and the rapid spread of electromagnetic energy were all far beyond what the models had suggested. The interactions with Earth's magnetic field were particularly surprising. The high-energy electrons spiraled along magnetic lines, creating a glowing sphere in space, which in effect produced a man-made aurora visible to millions of people far below. The scale of the light was so great that it temporarily blinded some sensors and cameras, and for a short while, the sky itself seemed to be alive with energy. The detonation of Starfish Prime also showed that space was not empty in the way people had assumed. It was not a passive void where explosions could happen without effect. The explosion demonstrated that even in the near vacuum of high altitude, nuclear detonations could produce electromagnetic pulses, charged particle clouds, and radiation belts that had real and measurable impacts on both technology and the environment. Satellites, which had been considered safe at that altitude, were suddenly vulnerable. Communications, navigation, and observation systems could be disrupted, sometimes permanently. What had been designed as an experiment to gather knowledge had turned into a display of the power humans could unleash on space itself. The sheer scale of the flash was unprecedented. People on islands far from Johnston Atoll described the light as brighter than the sun at noon, filling the sky in an expanding, glowing sphere that seemed to hang in place for seconds before dissipating. The combination of brightness, color, and motion created a spectacle unlike anything anyone had ever imagined, a human-made aurora in a sky that should have been black. Observers later described a sense of disbelief, some thinking that a meteor or a natural explosion had occurred. But it was not nature at work. It was the result of human technology, an experiment in power and physics, pushing the limits of what people knew about space, nuclear energy, and the Earth's own magnetic field. Beyond the visual effects, the explosion also sent shockwaves of particles racing through the upper atmosphere. Electrons, protons, and gamma rays moved outward from the detonation point, interacting with the Earth's magnetic field in ways that created unpredictable results. Satellites already in orbit experienced sudden increases in radiation, damaging solar panels and sensitive electronics. Some communications satellites, which had been providing early signals of global coverage, were knocked offline almost immediately. Scientists had not predicted the scale of the effect, and engineers scrambled to understand why systems that should have been safe at that altitude were failing. The detonation had introduced a new kind of hazard in space, one that could not be ignored in future satellite operations. As the sphere of charged particles expanded, it created a glowing halo that spread over thousands of kilometers, moving along magnetic field lines and interacting with the thin upper atmosphere. The light was seen across the Pacific, in places far beyond Johnston Atoll, startling observers who had no idea that a nuclear explosion could be visible so far away. The flash was not just bright, it was blinding in some areas, forcing people to look away, creating a surreal spectacle that was both awe-inspiring and terrifying. The energy released by the explosion was enormous, far beyond anything that had been safely tested before, and it made clear that detonation in space was not simply a scaled-up version of ground tests. In addition to visual and electromagnetic effects, the explosion sent high-energy radiation streaming along the Earth's magnetic field. These particles created temporary radiation belts that trapped charged electrons, forming man-made zones of energetic particles around the planet. Satellites that passed through these belts encountered levels of radiation far higher than normal, causing damage to circuits, sensors, and power systems. Some satellites failed completely, while others experienced temporary glitches. The unexpected persistence of these belts showed that nuclear explosions in space could have long-lasting effects that went beyond the initial flash, changing the environment around the Earth in ways that had not been anticipated. The detonation also had effects on Earth's own atmosphere, though subtle. High-altitude nuclear explosions release energy that interacts with gases, causing ionization and creating regions of charged particles that can affect radio transmissions. This was observed immediately after Starfish Prime, as some long-range communication systems experienced temporary disruptions. The energy from the explosion propagated across magnetic field lines, demonstrating that even in a thin, almost empty space, nuclear energy could have wide-reaching impacts. It was a moment that forced scientists and military planners to reconsider everything they thought they knew about space, explosions, and the way energy travels above the atmosphere. Starfish Prime was a test that broke every expectation. What was supposed to be a brief flash with minimal effect became a glowing spectacle seen thousands of kilometers away. What was supposed to be a contained experiment became a demonstration of electromagnetic power that affected satellites, electrical systems, and the Earth's near-space environment. The explosion showed that space was a live environment, full of energy interactions that could amplify effects far beyond what planners had imagined. Satellites in orbit were vulnerable, observers on Earth were stunned, and scientists realized that high-altitude nuclear detonations could not be considered safe or predictable. The shockwave of particles and radiation from Starfish Prime also revealed something entirely new about the way the Earth's magnetic field interacts with charged particles. As electrons and other particles moved along magnetic field lines, They created visible aurora-like patterns, spreading over areas far larger than the initial blast radius. This phenomenon was entirely unexpected. Scientists had anticipated some interaction with the atmosphere, but the scale, color, and persistence of the auroras exceeded every model and calculation. The event became a live demonstration of how powerful a human-made nuclear detonation could be when released in space, and it forced the realization that space was not empty or neutral, but a place where energy could move in ways that could be seen, felt, and measured across vast distances. Starfish Prime also set a new precedent for how humans could alter the near-Earth environment. The explosion created artificial belts of charged particles that did not exist before. These radiation belts lasted for months, posing a danger to all satellites that passed through them. Engineers were now faced with a problem they had never encountered. Space itself had become a hazardous zone because of human action. The explosion made clear that space was not just a neutral place for science and observation. It was an environment that could be manipulated, but manipulation came with risks that were enormous and unpredictable. The detonation at 400 kilometers altitude, inside what is considered low Earth orbit today, was not just a scientific experiment. It was a demonstration of human reach and human power. It showed that technology could send nuclear energy far above the surface of the planet, that energy could interact with the magnetic field, and that the consequences could spread thousands of kilometers away. People in Hawaii, watching the sky light up in colors they had never seen before, could not understand the full implications at that moment, but the scientists and military personnel involved understood that something historic had occurred. Even though the bomb exploded in a nearly empty region of space, the effects were immediate and wide-ranging. The flash, the sphere of charged particles, the visible aurora, and the electromagnetic disturbances all proved that nuclear energy behaves differently when released in the upper atmosphere. Ground observers, satellites, and instruments all recorded effects that had never been documented before. The detonation demonstrated that high-altitude nuclear explosions could affect both space and the planet below in ways that were far more complex than expected. Starfish Prime's detonation was also a lesson in unpredictability. Despite careful planning, simulations, and expectations, the explosion produced phenomena that no model had fully predicted. The massive expanding sphere of charged particles, the long-distance visibility of the flash, and the artificial aurora were all outcomes that shocked the scientific community. This single event revealed the limits of human understanding of space, energy, and nuclear reactions. It also highlighted the risks of experimenting with powerful weapons in an environment that was still largely unknown, and the detonation became a reference point for all future high-altitude tests, both in terms of what could be learned and what needed to be avoided. The event also made clear the power humans could project into space and the potential consequences of that power. Satellites in orbit, instruments on Earth, and communication systems all became part of a chain reaction caused by a single detonation. Starfish Prime was a moment when the boundaries of Earth, atmosphere, and space were blurred, when energy released by humans had effects far beyond what was imagined, and when the sky itself became a canvas for the unpredictable results of human experimentation. The detonation of Starfish Prime was not just a flash of light in the sky. It was a new chapter in human interaction with space. It showed that explosions in near-Earth space could create visible phenomena, lasting radiation belts, and electromagnetic effects. It proved that satellites and systems designed to operate safely at high altitudes could be vulnerable. It demonstrated that space is a connected environment where energy can travel and spread over immense distances. The event revealed the power, danger, and unpredictability of nuclear testing in space, and it set the stage for how humans would think about space, weapons, and the thin boundary that separates our planet from the void beyond. The detonation at 400 kilometers above the Pacific was a turning point. It was a controlled test that became an uncontrolled display of energy. The massive expanding sphere of charged particles, the blinding flash visible across thousands of kilometers, the artificial auroras in the sky, and the electromagnetic disturbances on the ground all showed that this was not a simple experiment. Starfish Prime demonstrated the power of human technology, the complexity of the near-Earth environment, and the risks of experimenting with nuclear weapons in space. The explosion reshaped the way scientists, engineers, and military planners understood the upper atmosphere, the magnetic field, and the potential consequences of high-altitude detonations. The sky over the Pacific on that day became a stage for the most dramatic demonstration of nuclear energy ever seen outside Earth's atmosphere. The explosion at 400 kilometers altitude created a spectacle that was both beautiful and terrifying. It lit up the night, it charged the environment with energy, and it created a phenomenon that would be remembered for decades. Starfish Prime was more than an experiment. It was proof that humans had the power to alter the space around their planet, with consequences that could be measured and felt far beyond the point of detonation. The combination of the rocket launch, the 1.4 megaton warhead, the altitude, and the unpredictable behavior of charged particles created a unique event in human history. The flash that was supposed to be brief became blinding. The minimal interaction with the atmosphere that was expected became a complex display of energy. The sphere of charged particles expanded in ways that no one could control. The detonation proved that nuclear explosions in space could not be treated as small-scale versions of ground-based tests. Starfish Prime was an experiment, a spectacle, and a warning all at once, showing the immense power of human technology and the complexity of the environment just beyond the Earth's surface. The detonation sent a clear message. Space is not empty, and energy released there can travel far, interact with the magnetic field, and have effects both visible and invisible to the naked eye. Satellites were damaged, radiation belts formed, the sky lit up with color, the flash traveled thousands of kilometers. The explosion was both a success in terms of scientific observation and a surprise in terms of scale and effect. Starfish Prime changed the way humans saw the upper atmosphere, the near-Earth environment, and the potential of nuclear energy beyond the surface of the planet. The artificial aurora. Beautiful, but wrong. After Starfish Prime detonated on July 9, 1962, the sky above the Pacific became something that no one had ever seen before. The initial blinding flash was only the beginning. Almost immediately after the explosion, the sky began to glow, not just for a moment, but for minutes, stretching longer than anyone expected. The colors were unlike anything that had been recorded during previous nuclear tests or natural auroras. Red, green, and purple hues shimmered and twisted across the horizon, creating an enormous, glowing spectacle that seemed alive. It moved, pulsed, and expanded in ways that mesmerized anyone who saw it. From ships scattered across the Pacific to islands hundreds and even thousands of kilometers away, observers were stunned. People described the sky as if it had been painted by some cosmic hand, a swirl of impossible colors that stretched farther than the eye could see. The phenomenon was not localized. It could be seen over huge distances, a reminder that what had been unleashed was far more powerful than a normal explosion. Scientists quickly realized that what people were seeing was not just a simple flash or residual glow. It was a complex physical process that began with the gamma rays released by the nuclear detonation. When Starfish Prime exploded at roughly 400 kilometers above Earth, it released massive amounts of high-energy radiation. These gamma rays, moving through the near vacuum of space, encountered traces of the Earth's upper atmosphere. Even at such high altitudes, there were still thin layers of gases, and when the gamma rays struck these gases, they produced high-energy electrons. These electrons were not ordinary. They carried energy far beyond what had been expected. They were injected into the near-Earth environment, creating a dense, expanding cloud of charged particles. These electrons did not stay in one place. Instead, they interacted with the Earth's magnetic field. Magnetic field lines, which normally guide charged particles from the Sun, captured the electrons from the explosion. Once trapped, the electrons began to spiral along these lines, moving back and forth in long arcs that connected the northern and southern hemispheres. As they traveled, they collided with other atmospheric particles, transferring energy and exciting the gases in the atmosphere. This excitation released photons, the very light that created the red, green, and purple glow seen for miles across the planet. What made this display so strange was how long it lasted. Unlike natural auroras, which move and shift over tens of minutes to hours, the artificial aurora from Starfish Prime remained highly visible for several minutes immediately after the detonation. The sphere of charged particles was enormous, expanding outward as it interacted with the magnetic field, giving the sky a layered, three-dimensional appearance. Observers reported seeing it pulse and shimmer, as though the sky itself were breathing, a reminder that the detonation had altered not just the atmosphere at one point, but an entire section of near space for a brief, dramatic moment. The colors themselves were unique. Red dominated large portions of the sky, stretching across the horizon like a curtain. Green, brighter and sharper, streaked through the red, appearing almost as sparks of light. Purple emerged in swirls and arcs, adding a layer of depth to the glow. The combination of these colors was both beautiful and unsettling. Unlike natural auroras, which are powered by solar particles and take hours or days to build and move across the sky, this phenomenon was entirely human-made, the product of a single explosion. It looked like nature, but it was not natural. It was a clear sign of how a nuclear detonation could reach into space and manipulate the environment in ways that had never been experienced before. Observers described the effect as surreal. Mariners at sea, stationed far from Johnston Atoll, reported a sky that seemed alive, shifting, and enormous. The colors were so intense that some people could not look directly at them. On islands hundreds of kilometers away, people awoke to strange glows in the sky, wondering if some cosmic event or meteor shower had occurred. Cameras captured the light, but the scale was hard to convey in photographs. It was not just a visual event, it was an atmospheric and electromagnetic event, showing a connection between space, the explosion, and Earth itself. The scientific explanation became clear as the data was analyzed. Gamma rays from the nuclear blast struck the upper atmosphere, producing high-energy electrons. These electrons moved along magnetic field lines, and as they interacted with atmospheric gases, photons were emitted, producing visible light. Essentially, the explosion created an aurora similar to those naturally caused by solar storms, but this one was artificially made. It was the first time humans had created a large-scale aurora, and it was entirely unexpected in both scale and intensity. Scientists had predicted some interaction with the atmosphere, but they did not anticipate that the colors would be visible for thousands of kilometers, or that they would last for minutes rather than seconds. The charged particle cloud from the explosion expanded outward from the detonation point, following the curvature of the Earth's magnetic field. This created a dome-like effect, making it appear that the sky itself was filled with a glowing sphere. As electrons spiraled along magnetic lines, they emitted more light, reinforcing the glow. This cascading effect amplified the visual impact, making the aurora more intense and more dramatic than any natural aurora witnessed at that latitude. The artificial aurora was also a warning, even if it was beautiful. While it captured the attention of observers for its colors, it signaled a massive injection of energy into the near-Earth environment. The high-energy electrons were trapped in the magnetic field, forming temporary radiation belts. These belts were hazardous to satellites, many of which had only recently begun orbiting Earth. Instruments recorded increased radiation levels that damaged electronics, solar panels, and sensitive circuits on these early satellites. Some satellites failed completely. The aurora visible in the sky was a sign of the danger that had also been introduced. What looked like beauty was in fact a marker of powerful and dangerous energy surrounding the Earth. The scale of the phenomenon was immense. Observers across thousands of kilometers saw the glowing sky. People in Hawaii, nearly 1,400 kilometers from Johnston Atoll, reported witnessing bright green and red lights that seemed to hover and expand across the sky. Ships at sea, islands far from the detonation, and remote observation stations all captured glimpses of the aurora. The fact that it was seen so far from the explosion demonstrated just how powerful the interaction between high-altitude nuclear detonations and Earth's magnetic field could be. The visual spectacle also revealed the unpredictable nature of high-altitude nuclear explosions. Scientists had models predicting some light, but not this intensity, not this scale, and certainly not the way the charged particles spiraled along magnetic lines to produce aurora-like effects. The interaction of gamma rays with the atmosphere and electrons with the magnetic field had created a display that no human or machine had fully anticipated. It was a vivid example of the complexity of space physics and how nuclear detonations in space could create effects beyond the original blast zone. The colors persisted for minutes, shimmering and expanding as the charged particles moved along magnetic field lines. Unlike ground-based nuclear explosions, where fireballs and shockwaves dominate, this detonation created energy patterns in 3 dimensions above the Earth. The glowing particles illuminated the upper atmosphere, making it possible for people far below to witness an event that technically occurred hundreds of kilometers above them. This gave the explosion a surreal quality. It was as if the Earth itself had become a canvas, painted in red, green, and purple by human hands. The red light came from the excitation of oxygen atoms at high altitudes. Green appeared from interactions of electrons with lower oxygen layers. Purple emerged from nitrogen interactions, combining with the other colors to create the layered and swirling visual display. Each color indicated a different interaction, a different energy pathway, and a different part of the atmosphere affected by the explosion. Together, they formed a sphere of light expanding outward, a glowing shell above the Earth that could be seen for miles and minutes, connecting space, atmosphere, and human technology in a single, visible moment. The aurora also changed the understanding of how nuclear energy could behave in space. Previously, the assumption had been that a nuclear detonation at high altitude would produce light and gamma radiation, but that it would be largely confined to the detonation zone. Starfish Prime disproved that. The gamma rays initiated particle cascades that moved along the magnetic field, creating an effect that was visible far from the explosion and persisted long after the initial detonation. It became clear that high-altitude detonations were not localized. They interacted with Earth's magnetic environment, creating widespread and long-lasting consequences. This artificial aurora was more than a scientific curiosity. It highlighted the dangers of nuclear explosions in space. The electrons trapped in the magnetic field formed temporary radiation belts, exposing satellites to conditions far beyond what they were designed for. Early communication and navigation satellites were damaged. The beauty of the aurora masked a destructive effect in near-Earth space. It was a visual reminder that what humans can see does not always tell the whole story of the energy involved, and that even spectacular beauty can be a warning. Observers who saw the sky light up across the Pacific were witnessing a phenomenon unlike any other. The dome of glowing colors moved slowly, pulsed, and shifted as the charged particles spiraled along magnetic lines. It was dynamic and alive, unlike any normal aurora. Scientists studying the data could see how gamma rays from the detonation produced electrons, how those electrons were guided by magnetic fields, and how their collisions with atmospheric particles released photons, creating the colors in the sky. The chain reaction of energy release and movement across magnetic lines turned a single detonation into a vast, multi-dimensional light show. The phenomenon lasted far longer than the initial flash, expanding and contracting as particles moved along magnetic pathways. Red, green, and purple lights dominated, forming arcs, waves, and swirling ribbons that stretched across thousands of kilometers. The display was unpredictable, shifting in real time as electrons moved and interacted with atmospheric layers. It became a live demonstration of physics in action, of the interaction between nuclear energy, atmospheric particles, and magnetic fields, all observable by human eyes from far below. The artificial aurora also created a sense of unease among scientists and military planners. While visually stunning, it proved that nuclear energy in space could have unintended consequences, affecting electronics, satellites, and the near-Earth environment. The gamma rays produced electrons that persisted, creating temporary hazards and altering the magnetic environment. It was a reminder that experiments in space carried risks beyond immediate detonation, and that human actions could reach into near space with unpredictable effects. Even though Starfish Prime had achieved its goal of testing high-altitude nuclear detonation, the artificial aurora was a phenomenon that no one had fully prepared for. It demonstrated the power of gamma rays, the behavior of electrons in the magnetic field, and the ability of human technology to create visible and lasting effects in the upper atmosphere. People thousands of kilometers away saw the sky glow in colors never before recorded. The phenomenon was beautiful but wrong. It was a warning and a spectacle at the same time, a reminder that what humans do in space can have both visible and invisible consequences across the planet. The glow of the artificial aurora faded slowly, leaving scientists and observers to realize that the near-Earth environment had been permanently altered in small but significant ways. The explosion created radiation belts, disrupted satellites, and showed how high-altitude nuclear detonations could produce effects far beyond their immediate zone. The gamma rays, electrons, and magnetic interactions that produced the aurora also set the stage for the challenges of space exploration in a nuclear age. The red, green, and purple lights were a visual signature of physics in motion. Gamma rays hit atmospheric gases, creating electrons. Electrons traveled along magnetic field lines. Collisions produced photons, and photons created visible light. The chain reaction was both simple in principle and extraordinary in outcome. From the detonation point above the Pacific, the energy spread, producing a glowing dome that could be seen across thousands of kilometers, lasting for minutes rather than seconds, pulsing, shimmering, and dancing in the upper atmosphere. The artificial aurora from Starfish Prime was unlike anything before it. The colors were intense, the scale massive, and the effects lasting. It showed that human technology could reach into space and manipulate energy on a scale that was previously unimaginable. The visible beauty of the aurora contrasted sharply with the dangerous reality of the charged particle clouds and radiation belts created. The sky over the Pacific on July 9, 1962, became a canvas of red, green, and purple, marking the first human-made aurora in history, a demonstration of power, physics, and unpredictability in the near-Earth environment. The EMP shock, when electricity failed. When the blast happened high above the Pacific, far beyond the reach of clouds and weather, far above the thin blue line that most people think of as the sky, something invisible moved faster than anything people could see. Faster than any sound, faster than any wave in the ocean, faster even than the blink of an eye. And that thing was an electromagnetic pulse, a sudden burst of energy that spread out in all directions at the speed of light, racing across space and down toward the Earth, carrying with it a force that would reach places no one expected and affect systems that were never meant to be touched by something happening so far away. This was not like a shockwave from a normal explosion on the ground, because there was no air at that height to carry pressure waves in the usual way, and there was no fireball rolling across land or sea. But instead, there was a surge of energy made of fields and particles, something that could pass through the air without being seen, something that could reach into wires, circuits, and systems, and something that could change the flow of electricity in a split second, turning normal operation into sudden failure. The people who planned the test knew that some kind of electromagnetic effect might happen, but what they did not expect was how strong it would be, how far it would travel, and how clearly it would show up in real life, not just on instruments or charts, but in the everyday systems that people depended on, systems that were built to handle storms, heat, and wear, but not a sudden pulse of energy coming from a nuclear blast in space. As the pulse spread out, it moved across the Pacific, covering huge distances in a fraction of a second, and when it reached the islands of Hawaii, it did not announce itself with sound or light, but with something far more strange, something that people could only understand after the fact, when things around them started to behave in ways that made no sense at first glance. Streetlights began to fail, not one or two, but hundreds of them, going out almost at once, as if someone had flipped a giant switch that controlled the whole island, and in total, around 300 streetlights were knocked out, leaving parts of the area in sudden darkness, even though there was no storm, no visible damage, and no clear cause that people could see with their own eyes. At the same time, telephone systems began to break down. Lines that were supposed to carry voices suddenly filled with noise or went silent. Connections dropped. Signals became weak or distorted, and operators who were used to dealing with normal issues found themselves facing something they had never seen before, a system-wide disruption that seemed to come out of nowhere and spread without warning. Burglar alarms also started to go off, not because of any break-ins or movement, but because the systems that controlled them were being hit by sudden changes in electrical flow, causing them to trigger as if they had detected danger, filling the air with unexpected noise and confusion, adding to the sense that something strange and widespread was happening all at once. All of these effects, the streetlights failing, the phones going silent, the alarms ringing, were not separate events, but parts of the same phenomenon, all linked back to the electromagnetic pulse that had traveled from the explosion site at the speed of light, reaching Hawaii almost instantly after the detonation, even though the blast itself had taken place far out in the Pacific and high above the Earth. The key to understanding what happened lies in the chain of events that started at the moment of the explosion, when the nuclear device released a burst of gamma rays, which are a form of high-energy radiation that can move through space and matter with great speed. And when these gamma rays reached the upper parts of the Earth's atmosphere, they began to interact with atoms in a way that set off a powerful reaction. The gamma rays struck atoms in the atmosphere and knocked electrons off them, a process that turned stable atoms into charged particles, and these freed electrons, known as Compton electrons, carried a great deal of energy, moving at high speeds and spreading out in large numbers, creating a cloud of charged particles that was both dense and fast-moving. These Compton electrons did not move in random ways, but were influenced by the Earth's magnetic field, which guided their paths and caused them to spread out in patterns that could cover wide areas. And as they moved, they created changes in the electric and magnetic fields around them, building up into a strong electromagnetic field that could interact with anything that carried or used electricity. The electromagnetic field generated by these moving electrons was intense, far stronger than what most systems on the ground were designed to handle. And when this field reached electrical systems, it caused sudden surges of current, spikes of voltage, and rapid changes that could overload circuits, damage components, or cause systems to shut down entirely. In Hawaii, this meant that the electrical grid, which powered streetlights and other systems, experienced sudden changes that caused some parts of it to fail, leading to the loss of those 300 streetlights. Each one a small point of light that went dark as the system feeding it was disrupted by the pulse. Telephone systems, which relied on long lines and sensitive equipment to carry signals, were also affected, as the electromagnetic pulse induced currents in the wires, creating noise and interference that disrupted communication, making it hard or impossible for calls to go through, and leaving people confused as to why their lines were no longer working properly. Burglar alarms, which were designed to respond to changes in circuits or signals, reacted to the sudden spikes caused by the pulse, interpreting them as signs of intrusion or damage and triggering alarms across different locations, adding to the sense that something unusual was happening even though the cause was invisible and far away. What made this event so striking was the distance between the source and the effect, because the explosion had taken place high above the Earth and far out over the ocean, yet its impact was being felt on the ground in a place like Hawaii, showing that the electromagnetic pulse could travel vast distances without losing its strength and could affect systems far from the original blast. The speed at which the pulse traveled also played a key role, because moving at the speed of light meant that it reached Hawaii almost instantly, leaving no time for warning or preparation, and causing effects that seemed to happen all at once, without any clear lead-up or sign that something was coming. This suddenness made the event even more confusing for those who experienced it, because there was no visible link between the explosion and the failures on the ground, no clear cause that could be seen or heard, only the results, which appeared as a series of unexpected disruptions across different systems. For scientists and engineers, however, the event provided clear evidence of how powerful an electromagnetic pulse could be, and how it could interact with real-world systems in ways that had not been fully predicted, showing that the models and assumptions used before the test had not captured the full scale of the effect. The role of Compton electrons in this process became a key focus, as they were the main drivers of the electromagnetic field that caused the disruptions, and understanding how they were produced, how they moved, and how they interacted with the Earth's magnetic field became essential for explaining what had happened. The chain reaction, starting with gamma rays, moving to electron release, and ending with the creation of an electromagnetic field, showed how a nuclear explosion in space could lead to effects on the ground without the need for direct contact or physical force, relying instead on energy and fields that could pass through space and air with ease. This realization changed the way people thought about nuclear weapons and their effects, because it showed that the impact of such weapons was not limited to blast and heat, but could also include wide-ranging effects on electrical and electronic systems, even at great distances from the explosion. The events in Hawaii served as a clear example of this, providing real-world data that could be studied and analyzed, and showing that even systems designed to handle normal conditions could be vulnerable to the sudden and intense effects of an electromagnetic pulse. The failure of the streetlights, the disruption of telephone systems, and the triggering of burglar alarms were all visible signs of a deeper and more complex process, one that involved high-energy radiation, charged particles, and electromagnetic fields, all interacting in ways that had not been fully understood before the test. The fact that these effects were observed in a populated area made them even more important, because they showed how such phenomena could affect daily life, not just in theory, but in practice, and highlighted the need to better understand and prepare for such events in the future. As data from the test was collected and studied, the details of the electromagnetic pulse became clearer, revealing how the initial burst of gamma rays led to the creation of Compton electrons, and how these electrons generated the intense electromagnetic field that caused the disruptions on the ground. This understanding helped to explain why the effects were so widespread and why they appeared almost instantly, as the speed of light allowed the pulse to cover large distances in a very short time, and the nature of electromagnetic fields allowed it to interact with systems across a wide area. The experience in Hawaii became a key reference point for studying electromagnetic pulses, providing real-world evidence of their impact and helping to shape future research and planning, as scientists and engineers work to understand how to protect systems from such effects and how to account for them in the design of new technologies. The events of that day showed that something happening far above the Earth could reach down and affect systems on the ground in a direct and measurable way, linking space and Earth through the movement of energy and particles, and demonstrating that the boundaries between different parts of the environment were not as separate as they might seem. The electromagnetic pulse from the explosion was not something that could be seen or heard, but its effects were clear and undeniable, showing up in the sudden loss of light, the breakdown of communication, and the unexpected noise of alarms, all of which pointed back to a single source, a burst of energy that had traveled across space and into the systems people relied on every day. The chain of cause and effect, from gamma rays to electrons to electromagnetic fields, provided a clear path for understanding what had happened, even if the scale and intensity of the effects had not been fully expected, and this understanding became a key part of the study of high-altitude nuclear detonations and their impact on the environment. The events in Hawaii were a reminder that even when something happens far away and out of sight, its effects can still be felt in real and immediate ways, especially when it involves energy that can move at the speed of light and interact with the systems that power modern life. The electromagnetic pulse created by the explosion showed that electricity, which is normally controlled and predictable, could be disrupted in an instant by forces that come from outside the usual environment, and that this disruption could spread across multiple systems at once, creating a wide range of effects from a single event. The failures and disruptions observed were not random, but followed from the underlying physics of the explosion and the interaction of radiation and particles with the Earth's environment, providing a clear example of how complex systems can be affected by events that occur far beyond their immediate surroundings. The biggest surprise: radiation belts. When the explosion happened high above the Earth, far beyond the clouds and far beyond the place where planes could fly, people expected light, heat, and the known effects that had already been studied. They expected flashes, signals, and measurable data. They expected things that would appear quickly and then fade away. But what they did not expect was something that would stay, something that would remain long after the light was gone, long after the moment of the blast had passed. What followed was not just a short event. It was not something that ended in seconds or even minutes. Instead, something new formed around the Earth itself, something invisible but powerful, something that wrapped around the planet and stayed there, changing the space environment in a way that had never been seen before. This was the biggest surprise. From the moment the explosion released its energy, a chain of reactions began in the space around Earth. High-energy particles were created in large numbers. These particles did not simply spread out and disappear. They did not drift away into empty space. Instead, many of them became trapped, held in place by the Earth's magnetic field, which acts like an invisible shield surrounding the planet. The Earth's magnetic field is not something people can see, but it is always there. It stretches far out into space and curves around the planet in smooth lines. Charged particles like high-energy electrons do not move freely through this field. Instead, they follow these curved paths, spiraling along the magnetic lines, moving back and forth between the northern and southern parts of the planet. When the explosion created a huge number of high-energy electrons, these electrons began to move along those magnetic paths. But instead of escaping, many of them became trapped in place, circling the Earth over and over again, forming a kind of ring or belt of energy around the planet. This was something very unusual. Scientists already knew that the Earth had natural radiation belts. These are known as the Van Allen radiation belts, and they are made up of charged particles that are held in place by the Earth's magnetic field. These natural belts had been studied, measured, and understood to a certain level. They were part of the normal space environment. But what appeared after the explosion was different. The explosion created artificial radiation belts, new layers of trapped particles that did not exist before. These belts were similar in shape and behavior to the natural ones, but they were created suddenly in a single event, and they contained particles that had been produced by the explosion itself. This was not something anyone had predicted. Before the test, scientists had ideas about what might happen. They expected radiation. They expected particles to spread out. They expected temporary effects, but they did not expect that the particles would become trapped in such a stable way, forming belts that would stay around the Earth for a long time. The fact that these artificial belts formed at all was surprising. But what shocked scientists even more was how long they lasted. These belts did not fade away quickly. They did not disappear after a few minutes or hours. They remained for months. For months, the Earth was surrounded by these extra layers of radiation, created by a single explosion. The high-energy electrons continued to circle the planet, moving along the magnetic field lines, bouncing between regions, and staying trapped in place. This persistence was unexpected. It showed that the space around Earth was not as simple as people had thought. It showed that once particles were placed into certain paths, they could remain there for a long time, held in place by forces that were not fully understood before. The trapped electrons carried a lot of energy. As they moved through the magnetic field, they created a region of intense radiation, one that could affect anything passing through it. This was not just a scientific detail, it had real meaning for anything that moved through space near the Earth. Satellites, for example, would have to pass through these regions, and these high-energy electrons could damage electronic systems, interfere with signals, and create problems that had not been seen before. The presence of artificial radiation belts meant that space itself had been changed, at least for a time. The idea that a single explosion could create a lasting structure around the planet was difficult to accept at first. It challenged the way people thought about space and energy. It showed that human actions could have effects that reached far beyond the immediate moment and far beyond the visible environment. The process that led to the formation of these belts began with the release of gamma rays from the explosion. These gamma rays interacted with atoms in the upper atmosphere, knocking electrons free and creating high-energy particles. These electrons then moved outward, guided by the Earth's magnetic field. Instead of escaping into space, many of these electrons became caught in the magnetic field lines. They began to spiral along these lines, moving in paths that kept them close to the Earth, forming layers of trapped particles that wrapped around the planet. These layers were not solid or visible, but they were real. They could be measured. They could be detected by instruments. They formed regions of space where radiation levels were much higher than normal. The similarity between these artificial belts and the natural Van Allen belts made the discovery even more interesting. It showed that the same basic processes were at work, but that they could be triggered in new ways. It showed that the structure of the space around Earth could be changed, not just by natural events, but by human actions. Scientists began to study these artificial belts in detail. They measured the energy of the trapped electrons. They tracked how the belts changed over time. They tried to understand why the particles remained trapped for so long and what factors might cause them to eventually fade away. What they found was that the magnetic field of the Earth was very effective at holding these particles in place. The electrons moved in complex paths, spiraling around magnetic lines while also drifting slowly around the planet. This motion kept them within certain regions, preventing them from escaping easily. Over time, some of the particles did lose energy. Some collided with atoms in the atmosphere and were removed. But this process was slow. It took months for the belts to weaken and fade, and during that time, they remained a strong presence in the space around Earth. The fact that this was not predicted made it even more important. It showed that there were gaps in the understanding of how radiation and magnetic fields interact. It showed that even well-studied systems could behave in unexpected ways when pushed beyond normal conditions. The creation of artificial radiation belts became one of the most important discoveries from the test. It was not something that had been planned. It was not something that had been expected, but it provided new information about the space environment and the behavior of high-energy particles. The discovery also raised new questions. If one explosion could create such belts, what would happen with more? How would multiple events interact? Could the space around Earth become filled with long-lasting radiation from repeated actions? These were questions that scientists had to consider as they began to understand the full impact of what had occurred. The presence of these belts also changed the way people thought about space travel and satellite design. it became clear that radiation was not just a distant concern, but something that could be altered and intensified, creating new risks for technology and exploration. The trapped high-energy electrons were not just passive particles. As they moved, they could interact with other systems. They could create secondary effects. They could influence the behavior of other particles. The belts became a dynamic part of the space environment, not just a static layer. The idea that space could be changed in this way was both fascinating and unsettling. It showed that the boundary between Earth and space was not fixed. It showed that events in one place could have lasting effects in another, linking the atmosphere, the magnetic field, and the wider space environment into a single system. The artificial radiation belts were a clear example of this connection. They were created by an event in the upper atmosphere, shaped by the Earth's magnetic field, and extended into space, forming a structure that could be detected far from the original explosion. As time passed, scientists continued to observe the belts. They watched how the intensity changed. They studied how the particles moved. They compared the artificial belts to the natural ones, looking for similarities and differences. This work helped to improve the understanding of how radiation behaves in space. It provided real data that could be used to test theories and refine models. It showed that the behavior of high-energy particles was more complex than previously thought. The fact that the belts lasted for months was one of the most striking aspects of the discovery. It meant that the effects of the explosion were not limited to a short time. They extended far into the future, creating a lasting change in the environment around the Earth. This persistence also meant that the belts could be studied over time, providing a rare opportunity to observe how such structures evolve. Scientists could track the gradual loss of particles, the changes in intensity, and the eventual fading of the belts. The discovery of artificial radiation belts was not just a scientific detail. It was a moment that changed the understanding of how space and energy interact. It showed that the Earth's magnetic field could trap particles in ways that were not fully understood, and that these trapped particles could remain for long periods. The unexpected nature of this discovery made it even more important. It showed that even in controlled tests, there could be outcomes that were not predicted, outcomes that revealed new aspects of the natural world. The belts themselves were invisible to the human eye, but their presence was real and measurable. They formed a hidden layer around the Earth, one that carried energy and influenced the space environment in ways that could not be ignored. Satellites start dying. High above the Earth, far beyond the clouds and far beyond anything people could see with their eyes, machines were quietly moving through space, following their paths around the planet, doing their jobs without sound, without attention, and without any sign that something was about to go wrong. These machines were satellites, and they were built to survive in space, designed to handle cold, heat, and the emptiness around them. They were not built for what was coming. After the explosion and the creation of artificial radiation belts, space itself had changed. It was no longer the same environment those satellites had been designed for. Invisible layers of high-energy particles now surrounded the Earth, and these particles were not harmless. They carried energy, and they moved fast, and they passed through anything in their path, including the satellites that were orbiting quietly through those regions. At first, nothing seemed different. The satellites continued their paths. Signals were still being sent. Data was still being received. But slowly, something began to change. The radiation was working. The high-energy electrons trapped in the artificial belts were constantly moving, constantly spiraling along the Earth's magnetic field. As satellites passed through these regions, they were exposed again and again, each pass adding a little more damage, a little more stress to systems that were never meant to handle such intense and repeated exposure. One of the satellites affected was Telstar 1. Telstar 1 was an important satellite. It was part of a new era of communication, a machine that helped send signals across long distances, linking places in ways that had never been possible before. It represented progress, technology, and the future of communication. But Telstar 1 was not prepared for the environment it found itself in. As it moved through orbit, it passed through the artificial radiation belts over and over again. Each time, high-energy particles struck its surface. Some of these particles passed through its outer layers and reached the sensitive electronics inside. Electronics are delicate. They depend on controlled flows of electricity, precise signals, and stable conditions. When high-energy radiation enters these systems, it can disrupt that balance. It can cause sudden changes in current flip bits in memory and damage components in ways that are not always immediate but build over time. For Telstar 1, this damage began to add up. At first, there were small issues. Signals became less stable. Systems did not respond as expected. There were interruptions that could not be easily explained. Engineers on the ground noticed these changes, but they did not yet see the full picture. The radiation continued to strike. Solar panels, which are used to collect energy from the sun, were also affected. These panels rely on materials that can convert light into electricity, but they are sensitive to radiation. High-energy particles can damage the structure of these materials, reducing their ability to generate power. As Telstar 1 continued its orbit, its solar panels began to degrade. They produced less power. The satellite had less energy to run its systems. This made it harder to maintain normal operation. At the same time, the internal electronics were being damaged. Circuits that once worked perfectly began to fail. Components that were designed to last for years started to break down much sooner. The damage was not sudden. It was not a single event. It was a slow process, one that happened over weeks and months, each pass through the radiation belts adding more harm. Eventually, Telstar 1 could no longer continue. Its systems failed. Another satellite, Ariel 1, faced a similar fate. Ariel 1 was also moving through the same space, passing through the same regions filled with high-energy electrons. Like Telstar 1, it had been designed for space, but not for this new, altered environment. The radiation affected Ariel 1 in the same way. Its electronics were exposed again and again, its systems slowly wearing down under the constant impact of high-energy particles. Signals from Ariel 1 began to show problems. Data became unreliable. Systems behaved in unexpected ways. Engineers tried to understand what was happening, but the cause was not something they had fully considered before. The artificial radiation belts were still there, still active, still filled with trapped electrons moving at high speeds. Each time Ariel 1 passed through these belts, it received another dose of radiation. The damage continued. Solar panels lost efficiency. Power levels dropped. Internal systems became unstable. The satellite struggled to maintain normal operation. Over time, Ariel 1 also failed. Then there was Transit 4B. Transit 4B was part of a navigation system, helping to provide positioning information. Like the others, it depended on stable electronics and reliable power. And like the others, it was not prepared for the intense radiation environment that now surrounded the Earth. As Transit 4B moved through orbit, it encountered the same belts of trapped particles. The high-energy electrons struck its systems, passing through materials, interacting with circuits, and causing damage that built up over time. The effects were clear. Electronics were damaged. Signals became weak or incorrect. Systems failed to respond properly. The satellite began to lose its ability to function. The solar panels also suffered. With reduced power, the satellite could not support all of its systems. This made the situation worse, as low power combined with damaged electronics created a chain of failures that could not be reversed. Transit 4B eventually failed as well. These were not isolated cases. They were part of a larger pattern. The artificial radiation belts created by the explosion affected many satellites, not just a few. The environment in orbit had changed for all of them, and many were passing through the same dangerous regions again and again. The impact was widespread. Around 1/3 of all satellites in orbit at that time were affected. This number was shocking. It showed that the problem was not limited to a single satellite or a single type of system. It was a broad effect, one that reached across different missions, different designs, and different purposes. Satellites that had been working normally began to show signs of damage. Some experienced minor issues, others suffered major failures. In many cases, the problems appeared slowly, making it harder to immediately connect them to the radiation belts. But as more data was collected, the pattern became clear. The artificial radiation belts were the cause. The high-energy electrons trapped around the Earth were interacting with satellites in ways that had not been expected. They were damaging materials, disrupting electronics, and reducing the lifespan of systems that were meant to last much longer. The degradation of solar panels was a key part of this. Solar panels are essential for satellites. Without power, nothing else can function. When radiation damages the materials in these panels, their ability to convert sunlight into electricity decreases. This means less power is available, and systems begin to shut down or fail. At the same time, the damage to electronics created additional problems. High-energy particles can pass through circuits and cause what are known as single-event effects. These can change the state of a system in an instant, flipping signals or causing errors. Over time, repeated exposure can lead to permanent damage, where components no longer work at all. For many satellites, this combination of reduced power and damaged electronics was too much to handle. They failed. The fact that these failures happened over months made them harder to predict. It was not a sudden loss of all satellites at once. It was a gradual process, where one system after another began to show problems, then stopped working. This gradual loss created uncertainty. Engineers had to figure out what was happening. They had to look at the data, compare the timing of failures, and understand the new environment in space. They had to realize that the space around Earth was no longer the same as before. The artificial radiation belts were still present, still active, still affecting anything that passed through them. The loss of satellites had real consequences. Communication was affected. Navigation systems were disrupted. Scientific missions were interrupted. The systems that depended on these satellites had to deal with unexpected gaps and failures. This showed that the effects of the explosion were not limited to the moment it happened. They extended into the future, affecting technology and systems long after the initial event. The idea that a single explosion could lead to the loss of multiple satellites over time was a powerful realization. It showed that changes in the space environment could have lasting and widespread impacts. The satellites that were lost were not just machines. They represented effort, time, and resources. Each one had been carefully designed, built, and launched. Each one had a purpose. And yet, they were all vulnerable to the same invisible threat. The artificial radiation belts created a new kind of risk, a risk that was not easy to see, a risk that did not act all at once, a risk that built slowly, quietly over time. As more satellites showed signs of damage, the scale of the problem became impossible to ignore. The number of affected systems continued to grow, and the connection to the radiation belts became clearer. This led to a deeper understanding of how space conditions can affect technology. It showed that satellites must be designed not just for the normal environment, but for extreme conditions as well. It showed that radiation can have long-term effects that are not immediately visible, but become serious over time. The events also highlighted the importance of understanding the space environment before placing systems within it. The artificial radiation belts were not part of the original design considerations for these satellites, and as a result, they were not prepared for what they encountered. The failures of Telstar 1, Ariel 1, and Transit 4B became clear examples of what can happen when technology is exposed to conditions beyond its limits. Each satellite told part of the story. Telstar 1 showed how communication systems could be affected. Ariel 1 showed how scientific missions could be disrupted. Transit 4B showed how navigation systems could fail. Together, they showed a larger picture. A picture of an environment changed by a single event. A picture of systems struggling to survive in conditions they were never meant to face. A picture of how fragile technology can be when exposed to forces that are not fully understood. The artificial radiation belts continued to exist during this time, continuing to affect satellites as they moved through orbit. Each pass through the belts added more damage, more stress, more wear. Some satellites managed to survive longer than others. Some experienced only minor issues, but many were not so fortunate. The number, about 1/3 of all satellites affected, remained a powerful measure of the scale of the impact. It showed that this was not a small or isolated problem. It was a major event in the history of space technology. The slow, steady loss of satellites over months created a lasting impression. It showed that the effects of radiation are not always immediate, but can build over time, leading to failure long after the initial exposure. The environment in space had been changed, and the satellites that were already there had no way to escape it. They continued their orbits. They continued to pass through the radiation, and one by one, many of them stopped working. Why it went wrong, the science failure. What made this event so important was not just what happened, but why it happened the way it did, because behind every unexpected outcome, there is a gap in understanding, a place where what people believed did not match what was actually true. And in this case, the gap was not small or simple. It was deep, and it touched the very way scientists thought about space, energy, and the environment around the Earth, leading to a situation where calculations, predictions, and expectations all fell short when they were tested against reality. At the center of the problem was an assumption, a quiet belief that shaped how everything was planned, a belief that space was mostly empty, that beyond the atmosphere there was very little to interact with, very little to influence how energy and particles would behave. And because of this belief, the models used to predict the outcome of the event were built on the idea that energy released in space would spread out, weaken, and fade without forming long-lasting or structured effects. This assumption seemed reasonable at the time because space does not have air in the same way the Earth's surface does. And without air, many of the familiar processes that people understand, like pressure waves or heat transfer through gases, do not occur in the same way. So it was easy to think of space as a kind of empty stage where energy could move freely without being shaped or held in place. But this idea was incomplete. The space near Earth is not empty in the way people once thought, because it is filled with invisible forces and fields, especially the Earth's magnetic field, which stretches far out into space and creates a structure that can guide and control the movement of charged particles. And this magnetic field is not weak or passive. It is active and powerful, shaping the environment in ways that are not obvious unless they are carefully studied. One of the key mistakes was underestimating how this magnetic field would interact with the particles created by the explosion, because when high-energy particles are released into space, they do not simply move in straight lines and disappear. Instead, they respond to the magnetic field, following curved paths, spiraling along magnetic lines, and in many cases, becoming trapped within certain regions. This trapping effect was not fully understood or fully included in the predictions, and as a result, the idea that particles would quickly spread out and lose their impact turned out to be wrong, because instead of disappearing, many of the particles remained, held in place by the magnetic field, forming structures that lasted far longer than expected. The concept of particle trapping is not simple because it involves the interaction between motion, charge, and magnetic forces, where a moving charged particle experiences a force that changes its direction, causing it to spiral rather than travel straight. And when this happens in the presence of a large-scale magnetic field, like the Earth's, the particle can become confined to a path that keeps it near the planet. This means that instead of energy being lost into space, it can remain close to Earth, circulating within the magnetic field, creating regions where particles are concentrated and where their effects can build up over time. And this was exactly what happened, even though it was not predicted with enough accuracy. Another major miscalculation involved the scale of electromagnetic pulse propagation, because while it was known that an electromagnetic pulse would be produced, the assumption was that its effects would be limited in range and intensity, and that it would not have a widespread impact on systems far from the source. This assumption was based on models that did not fully account for how the pulse would travel through the environment around Earth, especially at high altitudes, where the conditions are very different from those at the surface, and where the lack of dense air allows electromagnetic energy to move with less resistance and over greater distances. The pulse traveled at the speed of light, which means it spread across vast distances almost instantly, and because it was not significantly weakened by the environment it moved through, it retained enough strength to affect systems far away, leading to consequences that were much larger in scale than expected. The failure to accurately predict this scale was not just a small error, it was a fundamental misunderstanding of how energy moves in the space near Earth, where electromagnetic fields can extend over large areas and interact with systems in ways that are not limited by physical barriers. The belief that space would act as a kind of buffer, reducing the impact of the pulse, turned out to be incorrect, because instead of weakening the effect, the conditions in space allowed it to travel further and remain strong, reaching places that were not considered at risk. This connects back to the core assumption that space is empty, because if space were truly empty in the way it was imagined, then energy would behave in a simpler way, spreading out and fading, but the presence of magnetic fields and charged particles means that space is actually an active environment, one where energy can be guided, concentrated, and sustained. The idea of space as an active electromagnetic environment is central to understanding why the predictions failed, because it changes how energy and particles behave, turning what might seem like a simple release of energy into a complex system of interactions that can produce unexpected results. In this environment, particles do not just move freely, they are influenced by forces that shape their paths. And these forces can create patterns, structures, and long-lasting effects that are not obvious if one is thinking in terms of empty space. The miscalculations were not due to a lack of effort or intelligence, but rather to the limits of knowledge at the time, because while some aspects of the space environment were known, they were not fully understood, and the interactions between different elements, such as radiation, magnetic fields, and particle motion, were more complex than the models could capture. The underestimation of the Earth's magnetic field was particularly important, because this field is not just a background feature. It is a dominant force in the near-Earth environment, shaping how particles move and how energy is distributed, and failing to fully account for its effects meant that key processes were overlooked. The field acts like a guide, directing charged particles along certain paths, and in doing so, it can create regions where particles are concentrated, leading to higher levels of radiation and longer-lasting effects. And this guiding role was not fully included in the initial predictions. The trapping of particles, which led to the formation of artificial radiation belts, is a direct result of this interaction. And the fact that these belts persisted for months shows how strong and stable the trapping mechanism can be, something that was not expected at the time. The scale of the electromagnetic pulse and its ability to affect systems over large distances is another example of how the active nature of the space environment changes outcomes, because the pulse did not simply dissipate, it traveled through a medium that allowed it to maintain its strength and reach far beyond the immediate area of the explosion. All of these factors point to a common theme, which is that the models used to predict the event were based on an incomplete understanding of the environment, and as a result, they failed to capture the full range of possible effects. The assumption that space is empty led to simplified models, and these models could not account for the complex interactions that actually took place, leading to predictions that were too limited in scope and too optimistic in their expectations. When the event occurred, reality showed a different picture. one where the space near Earth is filled with forces and fields that can shape the behavior of energy and particles in powerful ways, creating effects that are both wide-ranging and long-lasting. This mismatch between expectation and reality is what defines the science failure, because it highlights the gap between what was believed and what was true, and it shows how important it is to fully understand the environment in which an event takes place. The lessons from this failure are not just about one event, but about the need to consider all aspects of a system, especially when dealing with environments that are not directly visible or easily understood, such as the space around Earth. The complexity of the electromagnetic environment means that simple assumptions can lead to large errors, and that detailed study and accurate modeling are necessary to predict outcomes with any level of confidence. The failure to fully account for particle trapping, magnetic field interactions, and the scale of electromagnetic pulse propagation shows how multiple small gaps in understanding can combine to create a much larger problem, one that only becomes clear when the event actually takes place. Each of these factors played a role, and together they created a situation where the effects were far greater and more persistent than expected, leading to consequences that were not planned for and not fully understood until after they occurred. The idea that space near Earth is an active electromagnetic environment changes the way events like this must be approached, because it means that energy released in this region will not behave in a simple or predictable way, but will interact with existing forces and structures, creating outcomes that can be complex and far-reaching. Understanding this requires a shift in thinking, from viewing space as empty to seeing it as a dynamic system, one where fields and particles are constantly interacting, and where new inputs of energy can lead to significant changes. The science failure in this case was not a single mistake, but a combination of underestimations and incorrect assumptions, all rooted in an incomplete view of the environment. And it serves as a clear example of how important it is to fully understand the systems being studied. The Earth's magnetic field, particle trapping effects, and the true scale of electromagnetic pulse propagation were all factors that needed to be considered in detail, and the failure to do so led to predictions that did not match reality. As a result, the event revealed new information about the space environment, showing that it is far more active and complex than previously thought, and that this complexity must be taken into account in any future work involving high-energy events in space. The recognition of space as an active electromagnetic environment is one of the key outcomes of this failure, because it provides a more accurate framework for understanding how energy and particles behave near Earth, and it helps to explain why the event produced such unexpected and far-reaching effects. This understanding also highlights the importance of continuous study and observation, because the space environment is not static, and new discoveries can change the way it is understood, leading to better models and more accurate predictions. The miscalculations in this case show that even well-planned events can produce surprises when the underlying assumptions are not fully aligned with reality, and they emphasize the need for careful consideration of all factors, especially in complex environments where many forces are at work. Human risk. What if astronauts were there? High above the Earth, far beyond the clouds, and far beyond the reach of normal human experience, there is a narrow band of space where humans can survive for a time inside machines, where astronauts live and work while circling the planet. And this region is not random or distant. It is close enough to Earth to still feel its pull, close enough to remain within the protective influence of its magnetic field, and close enough to be used again and again for missions. And this region sits at an altitude of around 400 kilometers, a height that may seem far, but is still part of what is known as near-Earth space, a place where human presence has become possible through careful design and planning. This altitude, around 400 kilometers, is not just a number, it is the same range where modern human space activity takes place, including the orbit of the International Space Station, which moves around the Earth at that height, carrying astronauts who rely on their spacecraft and its systems for survival. and who depend on the environment around them being stable enough to allow them to live, work, and return safely. Now, imagine that same region, that same altitude, not as a calm and controlled environment, but as a space filled with intense radiation, filled with high-energy particles moving at great speed, particles that cannot be seen or felt directly, but that carry enough energy to pass through materials, to enter the human body, and to cause damage at a level that is not just harmful, but potentially deadly. This is where the risk becomes clear. The artificial radiation belts that formed after the explosion were not located far away in deep space where nothing travels. They were formed around the Earth, within regions that overlap with the paths of satellites, and potentially with the paths of human missions, meaning that the same space where astronauts could be living and working could also become a region filled with dangerous radiation. At 400 kilometers, astronauts are already exposed to some level of radiation as part of normal space travel. Because outside the Earth's atmosphere, there is less protection from cosmic radiation and solar particles. But this normal level of exposure is understood, measured, and managed, with shielding, planning, and limits on how long astronauts can stay in orbit. What happened with the artificial radiation belts was very different. The levels of radiation created by the trapped high-energy electrons were far higher than normal, and they were not evenly spread out in a weak way, but concentrated in regions where particles were held in place by the Earth's magnetic field, creating zones of intense exposure that could affect anything passing through them. For a satellite, this meant damage to electronics and systems. But for a human being, the stakes are much higher, because the human body is not designed to handle high levels of radiation, and exposure can lead to serious harm in a short period of time. Radiation at high levels can damage cells, break down the structure of tissues, and interfere with the processes that keep the body functioning. And when the dose is high enough, the damage can be severe, leading to symptoms that appear quickly and that can become life-threatening. In the environment created by the artificial radiation belts, the exposure levels could reach potentially lethal doses, meaning that a human passing through those regions without adequate protection could receive enough radiation to cause serious harm or even death. This is not a gradual risk that builds slowly over years, but a situation where the intensity of the radiation is high enough that the effects could occur over a much shorter time, making it a direct and immediate danger to anyone in that environment. If astronauts had been in orbit at that time, moving through the same regions where the radiation belts had formed, they would have been exposed to these high-energy particles again and again. Each passed through the belts, adding to the total dose of radiation they received. And because the belts persisted for months, this exposure would not be a single event, but a repeated risk over time. The orbit of a spacecraft at 400 kilometers means that it circles the Earth many times each day, passing through different regions of space. And if some of those regions contain intense radiation, then the crew would be exposed repeatedly, with little time to recover and little ability to avoid the danger. Shielding inside a spacecraft provides some protection, but it is limited, especially against high-energy particles that can pass through materials. And while spacecraft are designed to reduce exposure, they are not built to handle extreme levels of radiation, like those created by the artificial belts. This means that the protection available to astronauts would not be enough to fully shield them from the danger, and over time, the radiation would penetrate the spacecraft, reach the crew, and begin to cause damage. The idea of potentially lethal doses is not an abstract concept. It is a measure of how much radiation the body can tolerate before serious effects occur. And when this threshold is reached or exceeded, the consequences can be severe, affecting multiple systems in the body and leading to a rapid decline in health. In such a situation, astronauts would not have the option to simply leave immediately, because returning to Earth requires careful planning, timing, and the proper conditions for re-entry. And if the environment in orbit has suddenly become dangerous, there may not be enough time to react before exposure occurs. The presence of artificial radiation belts would turn what is normally a controlled and predictable environment into one filled with hidden danger, where every orbit carries risk, and where the cumulative effect of repeated exposure could quickly become critical. This raises the stakes in a very direct way, because it shows that the consequences of the event were not limited to machines or systems, but could have extended to human life if the timing had been different, if astronauts had been present in orbit during that period. The fact that this region overlaps with the modern orbit of the International Space Station makes the scenario even more real, because it is not a distant or unlikely situation, but one that connects directly to current human activity in space, showing that the same conditions could affect missions that are taking place today. The thought of astronauts moving through a region filled with intense radiation, unaware at first of the full danger, relying on systems that are not designed for such conditions, highlights the seriousness of the risk and the importance of understanding the environment in which space missions operate. The artificial radiation belts created a situation where space itself became hazardous in a new way, where the invisible environment carried risks that could not be easily seen or avoided, and where the consequences of exposure could be severe and immediate. For humans, this kind of risk is very different from the risks faced by machines, because while a satellite can fail and be replaced, a human life cannot be treated in the same way, and the loss or harm of astronauts would represent a much greater consequence. The possibility of catastrophic outcomes comes from the combination of high radiation levels, repeated exposure, limited shielding, and the difficulty of immediate escape, all of which together create a situation where the margin for safety is very small. At 400 kilometers, astronauts depend on the stability of their environment, on the predictability of conditions, and on the ability to manage known risks. But when the environment changes suddenly and becomes filled with intense radiation, those assumptions no longer hold, and the systems designed for normal conditions may not be enough to ensure safety. The idea that the consequences could have been catastrophic is not an exaggeration, but a reflection of how serious the situation could become if humans were exposed to such conditions, especially over a period of time where the radiation belts remain active and continue to pose a threat. Each orbit through the belts would add to the total exposure, and without a way to avoid those regions, the crew would be placed in a position where the risk increases with every pass, turning time itself into a factor that works against them. The environment at that altitude would no longer be just a place of exploration and work, but a space filled with danger, where the invisible presence of high-energy particles creates a constant threat, one that cannot be seen but can have very real and serious effects. The fact that this situation was not fully predicted adds another layer to the risk, because it shows that the understanding of the environment was not complete, and that the possibility of such conditions was not fully considered when planning for human activity in space. This highlights the importance of studying and understanding all aspects of the space environment, including how it can change and how it can be affected by events, because without this understanding, it is difficult to fully protect those who operate within it. The scenario of astronauts being present during the formation of artificial radiation belts serves as a powerful example of how human life can be affected by changes in the environment, especially in a place where survival depends on careful control and protection. It shows that space is not just an empty area where humans can move freely, but a complex and active environment where conditions can change and where those changes can have serious consequences. The presence of high-energy electrons trapped around the Earth, forming regions of intense radiation, creates a situation where exposure is not just possible, but likely for anything passing through those regions, including human missions. The idea of potentially lethal doses emphasizes the severity of the risk, showing that the level of radiation is not just above normal, but high enough to cause serious harm in a relatively short time, making it a critical concern for any human activity in that region. If astronauts had been there, moving through the same paths as the affected satellites, the outcome could have been very different, because while satellites can fail without immediate loss of life, humans cannot be exposed to such conditions without serious consequences. The thought of such a scenario brings attention to the importance of understanding and controlling the environment in which space missions take place, and to the need for accurate predictions and careful planning to ensure that risks are identified and managed before they become real. The artificial radiation belts represent a change in the environment that goes beyond normal expectations, creating conditions that are more dangerous and less predictable, and showing that the space near Earth can be affected in ways that directly impact human safety. At 400 kilometers, the overlap between these belts and human activity creates a direct connection between the event and the risk to astronauts, making it clear that the consequences are not limited to technology but extend to human life as well. The idea that such conditions could exist for months means that the risk is not temporary but sustained, creating a period during which any human presence in orbit would be exposed to increased danger, and during which normal operations could become unsafe. This sustained risk changes the way such events must be viewed, because it shows that the impact is not limited to the moment of the explosion, but continues over time, affecting the environment and anything within it. For astronauts, this would mean operating in a space that is no longer stable, where each orbit carries risk, and where the cumulative effect of radiation exposure could quickly become critical, leading to outcomes that could be severe and potentially irreversible. Global response: end of space nukes. What followed after the full scale of the effects became clear was not immediate calm or simple acceptance, but a slow and serious realization that something fundamental had been misunderstood, not just in terms of science, but in terms of control, because the idea that such powerful events could be managed in a predictable and contained way began to fall apart when faced with the reality of what had actually happened, and this shift in understanding did not come from a single moment, but from a growing awareness across different groups of people who were studying the outcomes, comparing expectations with results, and recognizing that the gap between them was too large to ignore or dismiss. The central realization that began to take shape was that nuclear detonations in space were not controllable in the way they had once been believed to be. And this idea changed everything, because it challenged the assumption that such tests could be carried out safely or with limited impact, and instead showed that the environment in space, especially near the Earth, could respond in complex and unpredictable ways that extended far beyond the intended scope of any single event. This realization was not based on theory alone, but on direct observation of the consequences, where effects reached far across distances, lasted for long periods, and influenced systems that were never meant to be part of the experiment. And these outcomes made it clear that once energy was released in such a way, it could not be easily contained or reversed, and that the environment itself would carry and spread those effects in ways that were difficult to predict or control. As more information was gathered and analyzed, the understanding grew that space is not an isolated or empty place where actions remain local, but part of a connected system where changes can move across large areas and affect multiple layers of the environment. And this meant that a detonation in one location could have consequences in many others, creating a situation where control over the full impact was not possible. The idea of uncontrollability became the key point because it captured the essence of the problem, showing that the outcomes could not be limited to a defined area or time, and that the effects could extend into regions where they were not intended, affecting technology, systems, and potentially people. And this lack of control made it clear that the risks were far greater than previously understood. This shift in thinking did not happen in isolation, but spread across scientific communities, military planners, and political leaders, all of whom had to consider what these findings meant for future actions. And as the understanding deepened, it became harder to justify continuing with activities that could produce such wide and unpredictable effects. The recognition that space-based nuclear tests could create long-lasting changes in the environment including radiation belts and electromagnetic disturbances, added to the concern, because it showed that the impact was not limited to the moment of detonation, but could persist for months, affecting systems and conditions over time. This persistence meant that even after the initial event had ended, its effects would continue, creating ongoing risks and complications, and this extended impact made it even more difficult to manage or mitigate the consequences, reinforcing the idea that such actions were not controllable in any meaningful sense. As discussions began to take place about what should be done in response, the focus turned to limiting or stopping activities that could produce these kinds of effects, and this led to conversations about agreements, rules, and policies that could reduce the risk and prevent similar situations from occurring in the future. These discussions were shaped by the understanding that the environment being affected was not confined to a single nation or region, but shared by all, and that changes to the space around Earth could have global consequences, affecting systems and activities that crossed borders and connected different parts of the world. This global nature of the impact made it necessary to think in terms of collective action, where multiple countries would need to agree on limits and restrictions because the actions of one could affect many, and the risks were not something that could be managed by a single group alone. The process of moving from realization to action was not simple or immediate because it involved balancing different interests, priorities, and concerns, but the evidence of what had happened provided a strong foundation for change, showing that the risks were real and that they could not be ignored. Out of this process came the development of agreements aimed at reducing the use of nuclear tests in certain environments, particularly those where the effects could spread widely and become uncontrollable. And one of the key outcomes of this effort was the creation of the Partial Test Ban Treaty. The Partial Test Ban Treaty represented a significant shift in policy because it established clear limits on where nuclear tests could take place, based on the understanding that certain environments, including space, the atmosphere, and underwater regions, were too connected and too sensitive to allow such activities without causing widespread and unpredictable effects. By banning nuclear tests in space, the treaty directly addressed the issue of uncontrollability in the space environment, recognizing that once energy is released there, it can interact with the Earth's magnetic field, create long-lasting changes, and affect systems over large areas, making it impossible to contain the impact. The inclusion of the atmosphere in the ban reflected a similar understanding, that the air surrounding the Earth is a shared environment where effects can spread through currents and processes that are not confined to a single location, and that testing in this region could lead to consequences that extend beyond the intended area. The decision to ban tests underwater also followed this logic, because water is another medium where energy and effects can travel, potentially affecting marine environments and spreading beyond the point of origin, creating risks that are difficult to manage or predict. The treaty did not emerge from a single moment of decision, but from a process of growing awareness and agreement that certain types of actions carried risks that were too large and too uncertain, and that limiting those actions was necessary to protect the shared environment and the systems that depend on it. The understanding that space-based nuclear tests are uncontrollable played a central role in shaping this outcome, because it provided a clear reason for why such tests should not continue based on evidence and observation rather than speculation or assumption. This shift from belief in control to recognition of uncontrollability marked a turning point, changing how such activities were viewed and how decisions about them were made, and it showed that the limits of knowledge and prediction must be taken into account when dealing with powerful technologies. The Partial Test Ban Treaty became a formal expression of this change in thinking, setting boundaries that reflected the new understanding of the environment and the risks involved, and providing a framework for reducing the likelihood of similar events in the future. The ban on nuclear tests in space was particularly important because it addressed the environment where the most unexpected effects had been observed and where the lack of control had been most clearly demonstrated, making it a key focus of the effort to limit such activities. By establishing this ban, the treaty acknowledged that space is not a neutral or isolated setting, but a complex and active environment where actions can have wide-ranging and lasting consequences, and that these consequences must be considered in any decision to use such powerful technologies. The global response to the events showed that it is possible for understanding to lead to change, even when the initial assumptions prove to be incorrect, and that learning from unexpected outcomes can result in policies that better reflect the realities of the environment. The recognition that nuclear tests in space are uncontrollable did not just stop further tests in that region, but also influenced how people think about the use of technology in shared environments, emphasizing the need for caution, study, and cooperation when dealing with systems that can affect the world on a large scale. The treaty itself became a symbol of this shift, representing a move away from actions based on incomplete understanding toward a more careful and informed approach, where the limits of control are acknowledged and respected. The inclusion of space, atmosphere, and underwater environments in the ban showed that the concern was not limited to a single area, but extended to all regions where the effects of such tests could spread and become difficult to manage, reflecting a broad understanding of how connected these environments are. The process that led to this outcome was shaped by the events that revealed the true nature of the environment, showing that assumptions about emptiness and isolation were not accurate, and that the reality is one of interaction, connection, and complexity. This understanding made it clear that actions taken in one part of the environment can influence others, creating a network of effects that cannot be easily separated or controlled, and that this interconnected nature must be taken into account in any decision involving powerful technologies. The global response, including the creation of the Partial Test Ban Treaty, reflects this awareness and the desire to reduce the risks associated with uncontrollable outcomes by setting limits that prevent the most dangerous types of actions from taking place in sensitive environments. The ban on nuclear tests in space stands as a direct response to the realization that such tests can produce effects that extend far beyond their intended scope, affecting systems, environments, and potentially people in ways that are not predictable or manageable. By recognizing this and acting on it, the response marked a shift toward a more cautious and responsible approach, where the focus is on preventing harm and maintaining stability in environments that are shared by all. The understanding that space near Earth is an active environment where energy and particles interact in complex ways played a key role in shaping this response, because it showed that actions taken there can have far-reaching consequences that must be considered carefully. The policy shift represented by the treaty was not just about stopping certain tests, but about acknowledging the limits of control and the importance of understanding the environment, and using that understanding to guide decisions that affect the world on a global scale. The events that led to this shift provided a clear example of how unexpected outcomes can reveal gaps in knowledge and lead to changes in policy, showing that learning from experience is essential in dealing with complex systems. The recognition of uncontrollability, combined with the evidence of widespread and lasting effects, created a strong case for limiting nuclear tests in certain environments. And this case was reflected in the terms of the Partial Test Ban Treaty. The treaty's focus on banning tests in space, the atmosphere, and underwater environments shows a clear understanding of where the risks are greatest and where the potential for uncontrollable outcomes is highest, making it a targeted response to the specific issues that had been identified. This targeted approach allowed for a reduction in risk while still acknowledging the complexity of the situation, and it provided a framework for cooperation among different nations based on a shared understanding of the environment and the need to protect it. The global response to the realization that space nukes are uncontrollable demonstrates how knowledge can lead to action, and how the recognition of limits can result in policies that aim to prevent harm and maintain stability in environments that are essential to life and technology. EMP remains a serious military concern today because modern systems depend heavily on electronics, and satellites are now far more critical to everyday life through GPS, communications, and banking systems, meaning any disruption would spread quickly across the world and affect how people navigate, communicate, and handle money. A similar detonation today could disable global infrastructure on a massive scale and collapse satellite networks, because everything is more connected than before, and losing those systems would cause widespread failure across industries, countries, and daily life in ways that would be difficult to control or recover from. This was the first time humanity altered Earth's space environment, created radiation belts that did not naturally exist, and accidentally damaged its own technology, proving that actions in space could have lasting and unexpected consequences. We didn't just test a weapon, we changed the physics of near-Earth space, and we didn't fully understand it until it was too late.